All right, so let's get started with chapter 12, Saturn. So Saturn is a very large planet. In fact, it's the second largest planet in the solar system. One thing you'll notice about Saturn is that it's pretty spectacular by its own right, but in many respects, it's kind of like uh, Jupiter's somewhat less impressive version. So Jupiter has the best of everything, and Saturn has the same things, but not as impressive as Jupiter. Though in certain respects, particularly with respect to the ring system, Saturn is much more amazing than Jupiter. Anyway, so the mass of Saturn is 5.7 times 10 to the power of 27 kgs, and that is 95 times the mass of the Earth. So ME right here, I just learned today after starting to teach online since March. Just today I learned that you can make a mouse pointer with your finger. I had no idea that you could do that. Anyway, so ME right here is the mass of the Earth. Okay, so Saturn is 95 times or almost 100 times the mass of the Earth. How, uh, how many times more massive is Jupiter compared to the Earth? I would have asked this question in class, and I told you that this is one of the things that I'm going to force you to memorize. Jupiter is 318 times the mass of the Earth, right? So Saturn is much smaller than Jupiter. The radius of Saturn is 60,000 kilometers, whereas the radius of Jupiter was 71,000 kilometers. So it's about 9.5 times the radius of the Earth. The density of Saturn is very, very low. It's only 700 kgs per meter cubed, whereas the density of Jupiter was 1400 kgs per meter cubed. So density is really low. In fact, it's less than the density of water. The orbital period of Saturn is 29 Earth years, a little more than 29 Earth years. So 1 year on Saturn is 29 years on the Earth. Saturn is mostly made up of hydrogen, 96% hydrogen and 3% helium, just like Jupiter. And the most amazing thing about Saturn is its spectacular ring system. So this unbelievable picture was taken by the Cassini spacecraft, and it's actually not one picture, but it's a composite made up of several pictures taken by Cassini, which have all been put together to make this unbelievable picture. And you can see that this is a visible light picture. So this is exactly what it would look like to the naked eye if you were on the Cassini spacecraft. This is what Saturn would look like. You can see the ring system of Saturn. You can, even in this picture, you can see how intricately detailed the ring system is, and you can also see Saturn's shadow on its ring system. Anyway, so Saturn has differential rotation, just like Jupiter. So hopefully you remember what differential rotation is. It means that different parts of the planet rotate at different rates. So the equatorial region might rotate at one rate, the polar regions might rotate at a different rate. Obviously, differential rotation is not possible if you have a rigid object like the Earth. Cannot possibly have differential rotation because the Earth is a solid rigid object. But a gas giant like Jupiter or Saturn or Neptune or the Sun, objects that are made of gas can or fluids rather, it's quite possible that they might rotate. Different parts of those objects might rotate at different rates, and so that is differential rotation. And you can see that right here in the numbers. The equatorial region of Saturn, which is the midsection of the planet, takes 10 hours and 14 minutes to complete one rotation, whereas the polar region, the part of the planet near the poles, takes a little bit longer, 10 hours and 40 minutes. So it does not rotate as a whole. Just like Jupiter, the rapid rotation and low density would imply that there would be a bulge in the equatorial region of Saturn, right? However, we do see a bulge, but it's not as large as we would expect if Saturn were made up of entirely liquid and gas. So what do we conclude from that? We had this exact same situation in Jupiter, and so hopefully you remember what we concluded from that in the case of Jupiter. And just to repeat the question, we know that Saturn is made up of liquids and gas, right? So it's a gas giant. So if you have a ball of liquid and gas, and if you spin it very rapidly, then you would expect the midsection of the ball to bulge out, right? The equatorial region to bulge out. And we do see that happening in the case of Saturn, but it does not bulge out as if it does not bulge out to the extent that we would expect it to bulge out. So what does that tell us? It tells us that not all of it is liquid and gas, and it's possible that Saturn has a core, a hard solid core, just like Jupiter did. So that's what I mentioned over here. It's similar to Jupiter. We don't see enough flattening, so that indicates that there must be a solid core to the planet. Okay. What about the atmosphere of Saturn? The atmosphere of Saturn looks very similar to Jupiter. In fact, the corresponding picture for Jupiter, if you take a look at it, you'll see it's very, very similar to this picture. It's a little less colorful than Jupiter, and you don't have persistent weather patterns. Like on Jupiter, you have the giant red spot, for instance, which has been around for 300 years. On Saturn, you don't have very long-lasting weather patterns. So the temperature of the clouds of Saturn is a little bit lower than Jupiter because it's further away from the sun. You see various cloud layers, and those cloud layers are clouds of ammonia, ammonium hydrosulfide, and water ice. And so the clouds are at different heights because these different materials will condense out at different temperatures. So water condenses to droplets of, water vapor condenses to droplets of water, which become ice at a certain temperature. And then ammonium hydrosulfide condenses out at even lower temperatures. So you have the ammonium hydrosulfide clouds above that. And ammonia gas vaporizes out, condenses out at an even lower temperature than that. And that's why you have the ammonia ice clouds at the highest level. So you have these clouds, and we find that the atmosphere is 92% hydrogen and 7.4% helium. So and tiny bits of methane and ammonia. Okay. I'll just make one comment about these two numbers. One thing which I probably didn't mention when we discussed Jupiter is that Jupiter's atmosphere is also mostly made up of hydrogen and helium with trace amounts of other gases. And the percentages of hydrogen and helium are 86.1% hydrogen and 13.8% helium. So you can see that there is a difference in the amount of hydrogen and helium in both between Jupiter and Saturn. For Saturn, it's mostly hydrogen, 92% hydrogen and much less helium, whereas in Jupiter, you have more helium and less hydrogen. We will see that this does play a role in something later on. So just keep this little fact in mind, that there is much less helium in Saturn's atmosphere than there is in Jupiter's atmosphere. All right. Okay, so weather systems on Saturn are similar in many ways to Jupiter. This is a diagram of the wind patterns on Saturn. If you saw this wind pattern diagram on Jupiter, which is in my chapter 11 PowerPoint, you will see that there is a lot more east-west fluctuation. So here you don't have that much east-west fluctuation. So it's kind of similar to Jupiter, but not completely similar. You see a lot of bands and then oval storm systems and turbulent flow patterns. This should be patterns. similar to Jupiter. And you have some pictures over here. You can see these storms on Saturn. Here is a major storm that was seen by the Cassini spacecraft. And so this storm is sort of churning its way across the northern hemisphere of Saturn. And also leaving behind a tail wrapped around the planet. So it's a crazy, powerful storm system. All right. Now, what about the internal structure of Saturn? This picture might also give you déjà vu that you've seen something very similar in Jupiter. And it is quite similar to Jupiter, though there are some differences. So the planet is mostly made up of hydrogen. In the beginning, you have molecular hydrogen, which is just hydrogen gas, and then the density of the gas increases and increases. In the case of Jupiter, we saw that the gas will most likely turn into liquid hydrogen. So you're going to have a liquid of ocean of, an ocean of liquid hydrogen. And you probably have something similar in Saturn as well. So you have hydrogen in the form of gas or liquid, all the way up to a depth of around 30,000 kilometers. So at that depth, the temperature and the pressure are extremely high. And we know from the previous chapter that if you subject hydrogen gas to insanely high temperatures and pressures, then it turns into a strange form called metallic hydrogen. And hopefully you remember what metallic hydrogen is. It's a new form of hydrogen. I mean, it's a different form of hydrogen which we don't see on Earth anywhere, which is a very good conductor of electricity, right? So it's difficult to do that on the Earth because we are not able to exert such enormous temperatures, create such conditions of enormous temperature and pressure on the Earth. But I did mention that it was briefly accomplished in in the Argonne National Lab about 10 years ago. So anyway, at a depth of around 30,000 kilometers, you have the molecular hydrogen is in the form of metallic hydrogen. So then you have this metallic hydrogen region, and then you have the core of Saturn, which is believed to be hard, solid. So that's the only solid part of Saturn, the core. Okay, and it's most likely made up of rocky type of materials. Okay, now the surface temperature of Saturn is 97 kelvins. So we had seen for the case of Jupiter, this is stuff we saw in the last chapter. Surface temperature was 125 kelvins, but based off of the amount of sunlight that Jupiter receives and the amount of sunlight that it gives off, we had expected its temperature to be only 105 kelvins. So the fact that Jupiter had a higher temperature of 125 kelvins told us that it is radiating out more energy than it is receiving from the sun. In fact, it's radiating out twice as much energy as it is receiving from the sun. And we had done a little calculation in class and saw where that factor of 2 comes from. So that led us to question, where is Jupiter getting its energy from? And since we are reviewing, we might as well just review that. So where is Jupiter getting its extra energy from? It's from its energy that's left over from the planet's formation. So the core of Jupiter is very hot. That heat is still in the process of leaking out, and that is believed to be the reason why Jupiter seems to be giving off more heat than it is receiving from the sun. So this is just a review of what we saw in chapter 11. Okay, in the case of Saturn, the temperature is 97 kelvins. That is also much more than what we would have expected Saturn's temperature to be based on the amount of light that it gives off. In fact, in the case of Saturn, the fact that its temperature is 97 kelvins indicates, the fact that its temperature is 97 kelvins indicates that it is radiating 3 times as much energy as it absorbs, right? So in the case of Jupiter, Jupiter seems to be giving off 2 times as much energy as it's getting from the sun. Saturn is giving off 3 times as much energy as it is receiving from the sun. So the question is, where is it getting all this energy from, right? So the same question as in the case of Jupiter. Now, the issue is that Saturn, the explanation in the case of Saturn cannot be the same explanation as in the case of Jupiter, because Saturn is smaller than Jupiter, right? So Saturn has already probably cooled off, and all the heat from its interior, most of that heat is already gone. So unlike Jupiter, which is still giving off the heat left behind from the planet's formation, in the case of Saturn, all that heat is most likely gone, right? So Saturn has cooled down now. So where is it getting all this extra energy from in order to be able to radiate 3 times as much energy as it is receiving from the sun? The answer lies in something called helium precipitation. So please make sure you understand this. Helium is in the atmosphere of both Jupiter and Saturn, right? But what happens is when the temperature is low, then what happens is many gases will condense to liquid form. This is something that you're very familiar with. You know that water vapor is a gas, but when the temperature is low, water vapor will condense into droplets of liquid water, right? So that happens all the time on our planet. That's the reason that we've got clouds of water in the sky. Because the temperature is lower up in the sky, and so when the water vapor goes high up, it forms droplets of water, right? Now, something very similar happens with helium. So, helium in Saturn's atmosphere forms tiny droplets of liquid helium, and what happens to these droplets of liquid helium? They start falling, right? So, so Saturn has a steady rain of helium happening throughout its atmosphere. So you have helium droplets forming in the atmosphere of Saturn and constantly falling down. Now, what happens to these droplets of what happens to the droplets of water on the Earth that form in the clouds? So they fall to the Earth. They fall as rain, and then they fall on us and soak us. They fall on the ground, right? They fall on the trees. They basically hit the surface of the Earth. But does Saturn have a surface? The answer is no. Saturn does not have any solid surface. So where would these droplets of helium rain go? They would go all the way down to the core of Saturn, right? So they would go all the way down to the core of Saturn and would accumulate over there, right? And then the tremendous pressure at the core of Saturn would cause these droplets, cause the liquid helium to heat up, and that heat is gradually being radiated by the planet. And that's why the planet seems to be giving off 3 times as much energy as it receives from the sun. So the extra energy comes from the very hot liquid helium that is at the core of Saturn. So please make sure you understand this. I'll just go over this one more time. So the helium in the atmosphere of Saturn condenses to droplets of liquid helium. Helium gas condenses to droplets of liquid helium because the temperature is very low. So the liquid helium falls as droplets of helium rain, and this helium rain goes all the way down to the core of the planet. And there, the intense pressure and temperature makes it heat up, and that heat is gradually radiated in the form of and that heat is gradually radiated outwards, and that is Saturn's energy source. All right. Okay. The let's talk a little bit about the magnetic field of Saturn. The magnetic field of Saturn is much stronger than the Earth. It's about 1,000 times stronger than the Earth, but it's actually much weaker than Jupiter. It's only 1/20th of Jupiter's magnetic field, right? And what causes Saturn to have such a powerful magnetic field? it's because of, it's the same reason as in Jupiter. So Saturn has the metallic hydrogen in its inside it, and and it has a very rapid rotation. So it meets all the, it fulfills the three requirements for having a magnetic field, and so it has a very strong magnetic field. And what are the three requirements for having a magnetic field? We've gone over this many times. The first requirement is that the inside of the planet has to be made of something that's electrically conducting. And there has to be the electrically conducting material has to be mobile, so it has to be fluid. So for example, if it's a metal, then it has to be molten, right? And the third thing is the planet or moon has to be rapidly rotating. Saturn meets all of these. It's got an enormous amount of liquid metallic hydrogen in its inside it. The metallic hydrogen is fluid, so you can have convection in that layer, and the planet is rapidly rotating. So it meets all three requirements in order to have a magnetic field, and so it has a pretty strong magnetic field. And here you can see the auroras in Saturn, which are also in the ultraviolet, just like Jupiter's auroras, and they are formed from exactly this in exactly the same way as in Jupiter. All right, let's talk a little bit about Saturn's rings. So the ring system of Saturn is the most spectacular of all planets in the solar system. So the three rings that you can see from the Earth are called the A ring, the B ring, and the C ring. So these are the three that you can see from the Earth. And then um, in between the A and the B rings, you have this large gap, and that is called the Cassini division. And there are also some other gaps, like the smaller gap called the Encke gap, which you can see in the figure here. So this is not a figure, this is actually a photograph. You can see the V highlighted here. So these are the rings that you can see from Saturn, and you can already see that there is so much structure in these rings. You have these gaps in the ring systems. Okay, so the B ring is the brightest, followed by the A and the C rings. What are the rings of Saturn made of? This was actually a major mystery for quite a long time, because mathematicians had calculated that the rings cannot be made up of anything solid, they cannot be made up of anything liquid, they also cannot be made up of anything gas. So what could they be made up of? The mystery was solved by somebody named James Clerk Maxwell, a Scottish physicist, who suggested that the rings are actually chunks of material which are independently orbiting Saturn. And then we're using more advanced telescope data, it was found that that is true. The rings are actually made up of tiny chunks of ice which are all orbiting Saturn. So it's completely mind-boggling if you think of it. So this huge, gigantic ring system of Saturn is composed of tiny, of small pieces of ice which are all orbiting Saturn together. And the sizes of these ice chunks can be very tiny, about a millimeter, or they can be somewhat large, like over 10 meters. So each of these chunks of ice, millions and billions and gazillions of chunks of ice, all orbiting Saturn together, make up these rings.